And let's do a cosmology segment, as we've got 3 interesting stories to cover. So let's do it. Today we're not even going to pick a random number because it'll be a short cosmology segment. So we're not even going to go to the Neil Gorell Swift Bat X-ray Observatory and look up a random object because, well, perhaps there's nothing random in the universe. So here's an artist's rendition of Oumuamua. And you may be familiar with Oumuamua because people thought it was an alien spacecraft because of the reflectivity and other features of the way it accelerated as it left the solar system. So a new theory is that it's made of nitrogen ice. Yes, nitrogen ice. And if Oumuamua is made of nitrogen ice, that could explain how it accelerated, all because of the good old evaporation, the sublimation of ice, where ice turns directly from a solid to a gas. What you would see happen with dry ice in normal room temperatures is what you would see happening as a result of the solar wind striking these objects, and in any case, it creates jets, yada, yada, yada. Pluto's surface is made of nitrogen ice, or has nitrogen ice on it. And one of the new theories is that perhaps it's because Oumuamua, which is Hawaiian for scout or messenger, by the way, is perhaps made of nitrogen ice. Perhaps not an alien spacecraft after all, folks. Sorry if that disappointed you. And regardless of whether I believe it's an alien spacecraft or not, that's the story. You can find it on phys.org in the Astronomy and Space section. Next, let's talk about baryonic matter, as something's been stinking. Something's been stinking in the realm of cosmology. And one of those things is dark matter and dark energy, as there are issues as to how galaxies hold together and how they accelerate and how they rotate and so on when it comes to cosmology. And it's looking more and more like we're just not able to see all of the matter because it's not illuminated by bright things like the cores of galaxies, quasars, blazars, etc. And just a little consumer tip here. This is the halo. So we've got an image here of the Andromeda galaxy, and then you've got this halo. And a couple things about galactic halos. One, they're very difficult to see without doing a complicated and expensive study of the area around the galaxies to correlate them with percentages of gas, mostly hydrogen. But here's another thing I would like to just quickly bring up while we have this great image on the screen. So what you're looking at here is the Andromeda galaxy and how large its halo would be if viewed with the naked eye. Now, yesterday we talked about the size of Jupiter's magnetosphere, but we're not going to talk about the magnetosphere of Andromeda. We're going to talk about Andromeda's polar field. So in the center of the Andromeda galaxy, there's this spiral, and at some sort of an angle, there's most likely a jet coming out of this galactic core. I'm just going to draw it in like a little tornado here in 2 directions, assuming that it has a single core main feature. The Andromeda galaxy may be producing plumes of high-speed protons traveling in outward directions mostly, but also with some channels traveling backwards, and with connected train cars of electrons in between these little clouds. Usually what you see is a pulse. You'll see a pulse of material, and then a pulse of material, and then a pulse of material. And that's just the way plasma propagates through space. And I forecasted over 2 years ago that we would see multi-million light-year length jets coming out of these sort of features. And the next article is about just that. But before we do that, back to this one, baryonic halos. As we're not able to very easily see particles that are doing certain things like accelerating at extremely high speeds. And so this is how we get the argument about that dark mode matter and so on. But the point is, perhaps the universe is not made of any dark matter or dark energy, and everything is a lot simpler than it looks. So again, it's difficult to calculate how much regular old baryonic matter, things like protons and neutrons, are in a galaxy, especially if those things aren't interacting with anything, if they're not illuminated by local photons, for example. So in any case, this article is on phys.org in the Astronomy and Space section, and I'm going to move on. I don't want the cosmology segment or the daily space weather to be too long here. But the next one is more interesting to me. So this is located about 11 billion light years away, when the universe is believed to be only 2 billion years old, which means we're seeing light from an extremely organized set of galaxies. So this is a galaxy cluster. The name eludes me, but what you're looking at is a very, very long string of somewhat connected gas. So the galaxy halos that we were just showing you apparently are a little bit longer, which means they're probably also a little bit more massive. And when we're talking about things that are, well, tens of millions of light years in length, hold on, let me get the exact number. So yeah, that's believed to be about 11 billion light years away, as the universe is believed to be about 13 billion years old. But in any case, we see strings coming out of the poloidal fields of these galaxies that are apparently a little bit longer than folks thought. So, and I predicted this over 2 years ago. You can view our conversation with Gareth of See the Pattern, where he didn't listen to me about poloidal fields. I wonder if he's listening now. Probably not. But in any case, I don't really care, because I have the correct information and he has a bunch of nonsense about electric stars, something that aren't real. So in any case, these are ultra long filaments here, folks. And I just want to get the length of these, because astronomers have long assumed that billions of galaxies are connected by a huge cosmic web of gas flows. The web is difficult to see because it generates almost no light. Until now, only nodes in the cosmic web had been mapped using quasars, because quasar is like a flashlight that you're looking directly down the beam of. You're looking down the poloidal field. These supermassive black holes in the centers of galaxies whose surroundings emit enormous amounts of light, the light is often scattered by the cosmic web, making the web around the quasars visible. Unfortunately, quasars are rare. Moreover, they're located at nodes of the cosmic web. As a result, they provide a limited view. So perhaps that will get some wheels turning into the way galaxies interact with each other. They interact like particle beams with each other. Yes, they inject particles into the other galaxies, folks. It's a thing. I forecasted it years ago. And at least now, here's a mainstream article on phys.org. We're talking about many, many Milky Way galaxies in diameter here. I want to say like 50 Milky Way galaxies in diameter, but I don't want to give you the wrong number. So anyway, there's a very, very distant galactic cluster that we're looking at here, and really lengthy filaments, which are being ejected from, again, the poloidal field. So this is probably a jet right here, and this galaxy is probably oriented with its other jet sort of in this direction. You can see that jet right there, a nice straight line out of that particular area. And this explains why galaxies tend to be at 90-degree angles to each other. But without going further into that, it's another phys.org article. This one is Astronomers Map the Silk of the Cosmic Web. And that's today's Cosmology segment. Hope you enjoyed that one, if your brain wasn't completely fried from watching yesterday's. And I've been your host, Dan, a.k.a. smAsho. And don't forget to press like and subscribe if you're viewing the content on YouTube. Share with your friends, your foes, your science noobs, and your science pros.